Hello everyone, I hope you all are doing well. So this side Priya Bhatia, and in this particular video we will talk about the recurrence relation. Okay, so whenever we are talking about any recursive code, what is the meaning of recursion? The simple meaning is that when in the method definition a function is calling itself with a different set of parameters, right? So I hope that you already have been watched my recursion videos, right? So for every recursive code, we can create a recurrence relation. For example, you can refer my merge sort, my quick sort videos to understand this concept. Now the question is that, okay, once I will be able to generate a recurrence relation, how will I able to reach to a time and the space complexity aspect, right? So there are basically three methods that we have in the recurrence relation. That is substitution method, recursive tree method, and the master's theorem. So in this video, I will try to cover up all these three methods in a very detail with a set of examples so that you will get to know that how basically given a recurrence relation, we will be able to find out the time complexity with respect to that. So let's get started, and I hope that you will enjoy this video as well. So in this particular session, we will talk about that how we can solve any recurrence relation. I know that you are listening this word for the very first time. So let's talk about first of all that what is a recurrence relation, and afterwards we will see that how we can solve that using the different kinds of methods. Okay. So let's get started. Recurrence relation. Very important session. So whenever we are talking about a recurrence relation, this recurrence is coming from the word, from the key concept which is known as recursion. The question is, what is recursion? So whenever any function is calling itself directly or indirectly, this is something which we are saying as a concept of recursion. Okay. For example, I am saying that I want to find out the factorial of any given number. Suppose we want to find out the factorial of any given number. Now, for example, I hope everyone knows 5 factorial. So the answer should be 5 multiplied with 4 multiplied with 3 multiplied with 2 multiplied with 1. So it will be 20 into 3 is 60 into 2 is 120. So this is a kind of result that we are expecting as a output, right? Now what will happen is that in order to write the code, so basically what we are trying to do here is that in order to calculate any factorial of n, what we are trying to do is that we are doing n multiplied with factorial of n minus 1. This is something that we are trying to do here. So the base case, which is a case where my code will terminate, is something where I will say that when the value of n reaches to 0, or when the value of n reaches to 1, just you can return the answer as 1, right? You can return the answer as 1. So the recursion is that if suppose I am having one function named fact of n, right? Internally again I am calling the same function by the same name but with some different parameters, right? In order to calculate the factorial of a number. This is something which we call as a recursion. We will discuss a lot in depth about the recursion in our upcoming sessions, but I just want to give you a brief overview so that I will be able to explain what is recurrence relation. Now, for every recursive code, you will make some sort of recurrence relation where you will have the term which is repeated as t of something, right? So now what I will try to do is that I'll try to write the recurrence relation for you all, and then we will try to solve that given any recurrence relation, how we come up with a solution to find out the time complexity. For example, if I will write like this, that T of n, which is equals to, when the value of n is equals to 1, means when the number of elements present in an array or any kind of data structure that we are using is 1, then return 1. If the value of n is greater than 1, then return T of n minus 1 plus n, when the value of n is greater than 1. This is a kind of a recurrence relation, where this T indicates that this is a repetitive term. This is a repetitive function. This is something where recursion is happening. Okay? Now, we can solve any kind of recurrence relation using 3 methods mainly. One is called as a substitution method. One is called as a substitution method. Okay? One is called as a recursive tree approach. Recursive tree approach. And the last is something which we called as a master's theorem. So here we are having 3 main methods with the help of which we can solve any recurrence relation. Okay? So what we will try to do is that we will try to discuss each and every method step by step in every video. But I hope that you will be able to get an idea that what is recursion, first of all. Maybe not in that much depth, because I'll discuss with the proper code implementation in my later part of my video. But at least you will be able to get an idea that whenever a function, same function is calling inside the function definition, this is something which we are saying is a recursion. Apart from that, for every recursion, we are having a recurrence relation. Now, how we can generate any recurrence relation? Again, that also, please have a patience. We will study in our upcoming videos where we will talk about the algorithms, right? So what I will do is that usually I used to write the code and then I used to talk about the recurrence relation, how we can generate that. But as of now, in upcoming 3 videos where we will talk about the different methods, you just have to consider that a recurrence relation is given to us. Now the question is that given this kind of, so this is a kind of a, I would say, recurrence relation. This is a kind of a recurrence relation which is given to you. How it is forming up, that we will discuss. Don't worry. But in this particular case, what is our objective? Our objective is to find out the time complexity. Our objective is to find out the time complexity, right? So here, what we want to find out is the overall time complexity. So how, given a recurrence relation, we can reach to this time complexity aspect is our major objective. And in order to reach towards that point, we have these 3 methods: substitution, recursive tree, and the master's theorem. So now let's move towards the another video where I'll take maybe this same example and will try to show you that how I can solve this problem and will be able to find out the time complexity with the help of a substitution method. So in this particular session, we will talk about that how we can solve any recurrence relation with the help of a substitution method. Okay, so let's get started. So what I will do is that I'll try to take one example here, and with the help of that example, I'll try to demonstrate to you that how basically we can solve the recurrence relation using the substitution method. So let's get started. Okay, so substitution method. So suppose the given recurrence relation that is provided is T of n, which is equals to 1 when the value of n is equals to 1, and when the value of n is greater than 1, at that point of time it is equals to T of n minus 1 plus n. So this is a recurrence relation which is given to us. What is a recurrence relation and what are the properties of that? That we have already, I hope you guys have the clarity, we have understood in our previous part. How we got this recurrence relation, I will show you once we will reach towards the algorithms part. Then once we will be able to write any code, then I will try to show you that how we can get any recurrence relation. But as of now, just focus on this question that given any recurrence relation, so just you have to consider that, take a assumption as of now that this recurrence relation is given to you. This is already provided. Recurrence relation. Now, this is the assumption that we have. Now, for this particular case, what we can do is that when the value of t of n is equals to t of n minus 1 plus n, when I'm saying substitution method, it means that you need to substitute this recursive term. This is the term which is called as a recursive term. Means this is the function which is repeating itself, right? Now, just try to place instead of n as n minus 1 and do let me know what is the value of t of n minus 1. So I hope everyone agrees with me. If I will just place the value of with respect to n, instead of n, I will write n minus 1. So the value will be t of n minus 2 plus n minus 1, right? So basically what we are trying to do is that we are trying to here substitute the recursive terms, okay? We are trying to do that. Now, here just try to place this value of t of n minus 1 that we have in equation number 1 to this standard equation number 2. So we will get t of n as t of n minus 2 plus n minus 1 plus n, right? Now again, if I will try to place this value of t of n minus 2, or I will try to substitute this recursive term, in other words, it will be t of n minus 3 plus n minus 2 plus n minus 1 plus n, right? Now the question is that how many times do I place this value? How many times do I place this value? So here we will place the value, we will keep on doing the subtraction until suppose k times. Okay? Now this process will continue until or unless we will reach to a solution where instead of n, we are having the term as 1. Why 1? How this 1 is coming into picture? See the recurrence relation very much carefully now. What we are saying is that when the value of n is 1, the answer is 1 directly. It means that t of 1 is something which is equals to 1 here. So here if you will see, what we can write it as t of n minus k. So what is the value of k here? We can compute that the value of k is equals to n minus 1. So here t of n minus k plus, I can write n minus k plus 1. I can write n minus k plus 2 plus until so on, I can write n minus 2 plus n minus 1 plus n. I hope this makes pretty much sense to everyone. Okay, so now we know what is the value of k. So what we can do is that we will try to place this value of k as n minus 1. So we can say that t of n minus k value is n minus 1 plus n minus 1 plus 1 plus n minus 1 plus 2 until so on. We are moving ahead until we get n minus 2 plus n minus 1 plus the value of n, right? Now what I did is that I just placed the value of k as n minus 1. How this value of n minus k plus 1 is coming up? Just see the above pattern. Here the standard question says n minus 1 plus n, right? How this n is coming into picture? Can I say that this is nothing but n minus 1 plus 1? So this is nothing but n. Similarly, can I say that this is the term which is n minus 2 plus 1? So what we are observing here is that the next term corresponding to the recursive term t is n minus k plus 1. Similarly, when we are having n minus 3, so this term is nothing but n minus 3 plus 1. Can I say this? Right? Similarly, suppose we are repeating this step until k times, so we are getting n minus k plus 1. So here, if you will see, if I will try to solve this out, so we are saying that t of n minus n plus 1 plus n minus n plus 1 plus 1 plus n minus n plus 1 plus 2 plus n minus 2 plus n minus 1 plus n. Now if we will try to solve this, this is something which is not there. So this is something which is cancelled out with each other. So we are getting t of 1 plus this value is 2 plus this value is 3 until so on, plus the value of n minus 2 plus the value of n minus 1 plus n. Here we know that when the value of n is equals to 1, at that point of time, what is our result? Our result is something which is equals to the value as 1. So here we can just write the value directly as 1 here, plus 2 plus 3 until so on, plus n minus 2 plus n minus 1 plus n. This is something which you can say is a sum of, I hope everyone agrees with me, sum of n natural numbers. What are natural numbers? The numbers which are starting from 1, right, to infinite. So here if you will see, this is something which I can say is a sum of n natural numbers. Now can anyone tell me, this is the thing that we have already studied in our 9th, 10th, I would say lesser than that classes. What is the sum of n natural numbers? How can we compute that? It is nothing but is equals to, we have a formula n into n plus 1 divided by 2, which can be written as n square plus n divided by 2. Now if you have already watched my previous videos where I have already talked about that how we can compute any a priori analysis or how we can compute the time complexity, we have seen that while concluding any time complexity, we will just talk about the higher number, right? So here if you will see, we have n square plus n by 2. What is the higher exponent that we have? N square. So in terms of big O, the time complexity will be equals to order of n square. This is how basically with the help of a substitution method, we can solve any recurrence relation step by step. So the one thing that you have to take care of is that for a recursive term that you have, for example, in this question that is provided to us, this is the recursive term. So for the recursive term that we have, we will try to substitute it. Until what point of time? Until the point of time where the value, this is the somewhere you can say this is the base case condition. Until this base case condition will met. What is the meaning of base case condition? The simple meaning of base case condition is that at what point of time your code will terminate. And whenever you are writing any recursive code, you have to take care of this base case condition. Suppose if you're not writing any base case condition, what does that indicate? It indicates that your code is not terminating. And what are the properties of algorithms, by the way? One of the properties that we have studied is that our code or our algorithm will terminate after some point of time, after finite amount of time. If it is not terminating, it means it's not a valid algorithm. I gave one example as well, right? Where I have written inside the while loop the true condition, and inside that I printed my name. What I told you at that point of time that this is not a valid algorithm. Why is that so? Because it is not terminating. So in order to go for the termination of the code, we need to write the base case condition. And this is something which is telling us the base case condition. So for every recurrence relation that you ever met, you will always have the base case condition. Until that many number of times you have to repeat the task. After the final thing, you will always maximum number of times, specifically in substitution method, you will get some sort of series. You will get some sort of mathematical series. Now, these mathematical series can be anything. For example, here we are getting sum of n natural numbers. You might get any AP series. Again, these AP, GP we have already studied in our higher mathematics. 11th, 12th, I would say we have already understood this. Arithmetic progression or geometric progression, geometric series. So for these also you should be aware what is AP, what is GP, what is the formula to calculate the sum of AP series, what is the formula to calculate sum of GP series, right? Standard formulas you should know. What is the sum of n natural numbers, right? So after that, what you need to do is that you can take the higher exponent, because that is where we are talking about the approximation. That is where we are talking about the bigger time complexity. I hope that the concept that I want to explain here, that how basically we can solve any substitution method, is pretty much clear to everyone. What we can do is that we will try to solve few more examples. So this you can state as example number 1, which I have solved for you just to demonstrate you that how basically substitution method will work. In other video as well, upcoming video, I'll show you few more examples, and after that I'll give you some practice set questions which you have to do and tell me that what is the answer that you are getting. But before that, I'll show you few more examples, few more series, so that you will be able to get an idea that what kind of things can you can do with the help of the substitution method. So in this particular video, we will talk about another problem for the substitution method. I hope that before coming to this video, you have already watched my previous video where I have talked about the problem number 1, where we have seen that how mainly that substitution method will work. It's just that for the recursive term that we have, we need to substitute the values. That's what we have understood. And then we have to see that how many number of times we need to do the substitution. That is, what is the value of k? And I have showed you in that session that how we can basically find out the value of k. After this, we have already discussed that how we can make some sort of series, mathematical series, which we already aware about all those series in our lower classes, right? And after that, we can take or pick up the higher exponential term and we'll get the answer, right? This is what we have understood in our last session. Let's talk about another problem, which is again a very interesting problem, you will see. Okay, so let's get started with this session. So here what we can do, just give me 1 second. Here it is saying that the recursive term t of n, so the recurrence relation is t of n, which is equals to, again when it's a small problem, when the value of n is equals to 1, the answer is nothing but is constant, which is 1. But when the value of n is getting increment to greater than 1, the answer it says as t of n minus 1 plus 1 divided by n. So this is the problem statement that is given to us. So this is something which is a recurrence relation which is provided to us. Again, as I told you that how we are generating this recurrence relation, as of now don't care about that, because that thing in complete our course you will get an understanding once we get into the concept of any algorithm and data structure. But it's just that at that point of time when you will be able to generate a recurrence relation, you won't face any difficulty to get the time complexity part. That's why I am discussing this as a prior thing. Okay, so let's get started. Again, here if you will see, this is something, as I told you, that recurrence relation will happen only in the recursive codes, right? When there is a recursion. Now this is something which we can say is a base case condition. Base case condition. Every recursive code, whenever you will write any recursive code, you always have some base case condition. Means that is the condition where your code will get terminated, right? So now let's get started with the thing. So here we are having t of n, which is equals to t of n minus 1 plus 1 divided by n, right? Now what we can do is that we will try to substitute the value of t of n minus 1. So can anyone tell me what should be the value of t of n minus 1? It should be nothing but t of n minus 1 plus 1 divided by n minus 1. Here if you will see, I am just trying to understand the above pattern which is given in my question. This is the question which is given to me when the value of n is greater than 1. I am just trying to see the above pattern, and instead of writing this n, I am writing n minus 1 everywhere. Instead of writing n, we are just writing the value of n minus 1. I hope it's quite clear to everyone, right? So here we will be able to get the value as t of n minus 2 plus 1 divided by n minus 1. Now here if you will try to observe this, we can write this value of t of n minus 1 as this. So the second equation after doing the substitution will get t of n minus 2 plus 1 divided by n minus 1 plus 1 divided by n. Right? This is the thing that we are getting here. Now again what we can do is that we can again try to substitute the value. So this is the second equation that we are getting for a second time. Right? Third thing, when we do the same thing third time, obviously now if I will try to substitute the value of n minus 2 here, so I will for sure will get t of n minus 3 plus 1 divided by n minus 2 plus remaining two things will be as it is, plus 1 divided by n minus 1 plus 1 by n. Here if you will try to see, this is the third equation that we are getting for doing this thing third time. Now the question is that how many number of times I will repeat the same task. It's not like first, second, third, fourth, 10th. I don't want to waste my time to do the same thing again and again. The question is, how many times do I suppose to do the same task? So suppose we are doing the same task until k times. So here if you will see, I know the value of t of 1. The value of t of 1 is something which is equals to 1 here. So here we can say that I will do the same task until n minus k times. So when the value of k is, we are doing the same task k number of times. It's like when we are doing 2 times n minus 2, 3 times n minus 3. When we are doing k times, so it will be n minus k, whose value I want to be equals to 1, because that is the terminating condition, that is the base case condition that we have. So here the value of k will become n minus 1. The value of k will become n minus 1. It means that we need to do the same task until n minus 1 number of times. Right? So if we are doing the same task until k times or until n minus 1 number of times, at that point of time the value of t of n will become t of n minus k, right, plus 1 divided by, here if you will see, always and always we are getting the number in the denominator as n minus k plus 1, because here if you will observe, this is nothing but n minus 3 plus 1. Similarly in above case it will be n minus 2 plus 1. So here the value should be, n minus k plus 1 plus again 1 divided by n minus k plus 2, until so on the same thing will get repeated until we are getting 1 divided by n minus 1 plus 1 divided by n. Here now what we can do is that we can just try to replace this value of k with n minus 1. So we are getting the value as t of n minus 1, right, plus 1 divided by n minus 1 plus 1 plus 1 divided by n minus 1 plus 2 until the value of 1 divided by n minus 1 plus 1 divided by n. Here if you will try to see, the value is n minus n plus 1, which is equals to t of 1, right, plus this value will become n minus n plus 1 plus 1. So n and n will cancel out with each other. We will get the value as 1 divided by 2. Then we will get 1 divided by 3. You can just try to solve this. You will get 1 divided by 4 until so on, until the value of 1 divided by n minus 1 plus 1 divided by n. Here we know that when the value of n is equals to 1, the value will become 1, right? Because we know that the value of t of 1 is equals to 1 here. We already aware about this concept. So what we can do here is that we can try to just replace this value of t of 1 with 1 here. Plus we are getting the same thing. We can write it as it is, 1 by 2, 1 by 3, 1 by 4 until so on, until the value of 1 divided by n minus 1 plus 1 divided by n. So here if you will see, this is a kind of series. Is anyone aware about what this series is all about? Just think over it, just pause the video, take your time and do let me know what is your answer. This is a very famous series which is nothing but is a logarithmic series. That's why the overall time complexity that you are getting for this recurrence relation will be order of log of n. These are the kind of things which are very important, because everyone I have seen is easily able to generate the recurrence relation. But what sort of approach do we use basically to solve that recurrence relation to reach to a final big O time complexity, which we are reaching here? So this is nothing but big O time complexity, which will talk about a worst case scenario. That's where our target should be, right? So this is how basically we can do the thing with the help of a substitution method. I hope you guys find it very much easy and interesting, right? But apart from that, we do have two more methods which I have already illustrated in our previous video as well. And we will discuss those methods also in very much detail. Don't worry about that. But yes, I hope that this question which we have discussed in this session is pretty much clear to everyone. I'll try to solve few more problems on this method, and then we will try to go towards the recursive tree approach, okay? With the help of which we can solve different kinds of recurrence relation where we are having a multiple recursive terms. By saying that, here you will observe that we are having only single recursive term. Whenever we are saying t, whenever this term is repeating, just try to understand this is something which you can say is a recursive term here. So when you are having multiple recursive terms, then that recursive tree approach will be very much beneficial for us. But anyhow, we will discuss that in very much depth in the upcoming video. So this is the last problem that I want to discuss here using the substitution method. And maybe after solving these three problems, you will get an intuitive idea that how basically we can solve any recurrence relation using a substitution method. Okay, so let's get started with the today's session. Here again, we are having a recurrence relation which says that the value of t of n is something which is equals to 1 when the value of n is equals to 1, and the value of n is greater than 1 when the value is, or the recurrence relation is t of n by 2 plus n. So this is a kind of a recurrence relation that we have. Now again, this recurrence relation we need to solve using a substitution method. Now I am expecting everyone to please pause this video as of now, take this question and try to solve it on your own, and do let me know that what answer you are getting, okay? Because I think now the approach, the way we used to solve any recurrence relation using a substitution method is already conveyed in the above two videos, right? So the same method, same thing you need to do. It's just that instead of substituting that n minus 1 or n minus 2, here we need to substitute the value of t of n by 2. So let's get started. I hope that everyone already have tried it once. So t of n is something which is equals to t of n by 2 plus the value of n. Now what we can do is that we can try to solve the value for t of n by 2. It is something which is equals to t of n by 2 to the power 2 plus n by 2. What I am doing is that by seeing the above pattern, I am just trying to what I can say substitute the value for t of n by 2. Now it means that what I am getting as t of n, which is equals to t of n by 2 to the power 2 plus n by 2 plus the value of n. That's what we are getting when we are trying to substitute here for the two times. First time we are having this equation, right? This is for the first time. Second time we are getting this kind of equation. Okay, this is for the second time. Now for the third time, what will happen is that we will be able to get, now we need to substitute this value t of n by 2 to the power 2. So here basically what will happen is that it's 4, right? Now we need to divide it again by 2 in order to do the substitution. So it is nothing but is equals to t of n by 2 to the power 3 plus something which we are getting as n by 2 to the power 2 plus n by 2 plus the value of n. This is something which we are getting for the third time. Now again the same question I can ask from you, that how many times do we divide this value of 2, right? Again and again. It means that at what point of time this n by 2 to the power k is equals to 1, because 1 is something which is the base case condition in our question. This is something which is I can say base case condition, right? If this is the base case condition, so this is what we can write here. Now here if you will see, n is something which is equals to 2 to the power k. So the value of k is something which is equals to log of n base 2. This is something which we are getting. Okay, fine. So here the value of t of n is something which is equals to, it means that we need to repeat this same experiment log of n base 2 times, right? So here t of n by 2 to the power k plus, by seeing just the above pattern, I am getting a sense that it should be t to the n by 2 to the power k minus 1, right? Plus n by 2 to the power k minus 2 until so on, and we are getting at a very end the result is n by 2 plus n. Here we can just try to replace this value of k with the value which is log of n base 2, which we have already evaluated. So here the value of t of n is something which is equals to t of n by 2 to the power log of n base 2 plus n by 2 to the power log of n base 2 minus 1 plus n by 2 to the power log of n base 2 minus 2 until so on plus n by 2 plus n. Now here if you will see, what we can do is that we will be able to get the value as t of 1 plus, here what we can get is we can take the value of n as common, and here again we are getting something called as 1 divided by, again see why we are getting this one. Let me try to first of all, I think maybe maximum students will not able to get an idea how I am writing this. So this n and 2 can be interchanged with each other. So here what we will be able to get is n log of 2 base 2, and when the base and the coefficient that we have here is same, the value will be equals to 1. That's why we are getting the value as n. That's why we are getting the value as n here. So n divided by n is something which is equals to 1 here. Now what we can do is that we can write the same thing in this format: 1 by 2 to the power 0 plus 1 by 2 to the power 1 until so on divided by 1 by 2 log of n base 2 minus 1. Minus 1. How we are getting this? What we have did here is that we have tried to just take the constants, focus on this part in the reverse order. So what I did is that I tried to take the constants in a reverse order. So it's n plus n by 2 plus n by 2 to the power 2 until so on, until n by 2 to the power log of n base 2 minus 1. So what I did is that I just took the n as coefficient. When we take the n as coefficient, it will be 1 by 2 to the power 0, 1 by 2 to the power 1, 1 by 2 to the power 2, until what value? Log of n base 2 minus 1. Can I write like this? I hope this is making sense, right? So basically this value will become t of 1, and this particular portion that I am writing here, we have written in the form of a reverse order. We have written in the form of a reverse order. So that I want to show you here something. Here if you will observe, this is something which we called as a GP series, where the common ratio R value is 1 by 2. How we calculate the common ratio? It is nothing but 1 by 2 to the power 1 divided by 1 by 2 to the power 0, right? So here common ratio is 1 by 2. Now this is a sum of GP series where the value of R is less than 1. Now if you refer your I think 9th, 10th or 11th, 12th classes, here we have understood that the sum of GP series when the value of R is less than 1 is something which is equals to A into 1 minus R to the power n divided by 1 minus R. This is the sum of a GP series that we have. Now here if you will see, what is the value of A? A is something which is the first value which we have in our series, which is nothing but 1 here, because A is nothing but 1 by 2 to the power 0, which is something which is equals to 1 here. Now what we can do is that t of 1 we already know is equals to 1 only. It's a constant term. So 1 plus, what is the value of A? It is 1 into 1 minus 1 by 2 to the power n. Here if you will see, what is the value of n that we have? How many number of terms that we have? Approximately equals to log of n base 2. Can we write like this? Log of n base 2 divided by 1 minus 1 by 2. Here if you will try to solve this equation, this GP series equation, for sure if you will see here, and obviously outside this there is a n term which is already in a multiplication term. Now here if you will try to solve this particular series, you will be getting a constant value. So here what I am saying is that 1 plus any constant, suppose which I am representing as 1 only, into n is something where we need to take the higher factor in order to calculate the big O time complexity. So this is something which we are getting as a big O of n. So if you will try to see here, what we have did so far is that in any of the substitution method, whenever any problem is provided to you, the first step that you have to do is that when just you have to look for a recursive term. That what is the recursive term which is present inside my recurrence relation, right? There is always some recursive term. That's why there is the recurrence relation. Now what you have to do is that you need to substitute that recursive term again and again. But after, just you have to see the pattern here. By seeing or looking into the pattern, you will be able to get the substitution value. But now you have the major objective here is to find out that what is the value of k. This is very important to find out, because until what point of time do I suppose to substitute in a substitution method? This is what you will be able to get when you know the base case criteria or base case condition. That what is the point where it is terminating? What is the point where I should write this value as 1? Because I know when the value of n is 1, the value will be equals to 1 here. So that's why we took like this as a base case condition. Now with the help of these values, you will be able to somehow get the value of k, and until that point of time you need to write the values. Now you always get somewhere or the other in a substitution method a series, which is somewhere a mathematical series you will be able to get. Whether it is a AP series, GP series, or any logarithmic series or exponential series, or maybe sine, cos, or maybe sum of n natural numbers. So these things you should know. These are the very basic things. So basic I am saying series you should be aware of. Once you will get an idea about that, you will be always having that higher term. You need to see the higher I would say exponent term, or higher term, higher degree, right? So here you need to see that, and whatever you are getting here will be your final time complexity that you will be able to get here, right? That is the simple approach to solve any recurrence relation with the help of a substitution method. And that is what I think I have conveyed with the past 3 videos which I have created here, so that you will be able to get a clear-cut idea that how basically the substitution method will work. Now in the next upcoming video, what I will talk about is that how basically the recurrence relation can be solved using a recursive tree approach, and when basically we should go for that particular method instead of going for a substitution method. So in this particular session, I'll talk about that how we can solve any recurrence relation using recursive tree approach. Until now, so far we have discussed that how we can solve any recurrence relation using a substitution method. And I hope that with the help of the 3 examples or the problems that we have solved until so far, you must get the clarity that how we can substitute any recursive term via a substitution method. Here, let's now talk about a recursive tree approach. This is the second approach to solve any recurrence relation, right? So this is the approach called as recursive tree approach. Okay. Now in this approach, if you will see, whenever we are talking about a recursive tree approach, it is beneficial only when you have more than, if you have more than one recursive term in a recurrence relation, right? If you have more than one recursive term in a recurrence relation. Now, how basically this is happening? Let's try to understand this part. For example, a given recurrence relation which is given to you is that the value of t of n is something where I am saying, again, when it's a small problem, when the value of n is 1, you can get a constant time complexity. But when the value of n is greater than 1, at that point of time, suppose your time complexity or recurrence relation will be t of n by 5 plus t of 4n by 5 plus the value of n. This is a kind of a recurrence relation that you have. So if you remember, until so far we have discussed about substitution method, and there we have seen that there is only single recursive term that we have in terms of this t. This is a term called recursive term, right? That's what we have understood. Now, how basically, if suppose we are having more than one recursive term, how basically we can solve that? There is only one method with the help of which you can solve, and that is what we are discussing today, recursive tree method. So here if you will try to observe, we are having the value of t of n, and what we are trying to do here is that we are trying to basically dividing our data into basically three parts, I would say. Or in other words, I can say that suppose we are having a n size elements, obviously n is the size of the elements. Now here if you will see, what we are trying to do is that we are dividing our that n size array. You can consider any kind of data structure with which we are storing those n elements, and we are splitting those n elements into two halves. One is the n by 5, another one is the 4n by 5. And the cost required to split these elements into two halves, n by 5 and 4n by 5, is something which we are saying as n here. Can I say this? This is the actual meaning of this statement, where I am saying that we are dividing the complete n size elements into two halves. On the left side we are having n by 5, on the right side we are having 4n by 5, and the cost required to do this particular split is n. Now again, if you will see, the same thing we can do again, but now the way is somewhat different. Here again what we are trying to do is that we are again trying to divide our array into two halves. Now just try to understand the pattern here. When I am dividing my array into two halves, if you will observe on the left side, what we are doing is that we are dividing the array by 5, right? Whatever element we have, we are dividing that with 5. So that is the thing. And on the right side, what we are trying to do is that we are trying to multiply with 4 by 5, or in other words, I would say dividing it by 5 by 4. So again it will be n by 5 square, or it will be 4n by 5 square. Similarly here also, on the left side it will become 4n by 5 square, and on the right side it will be 4 square n by 5 square. I hope that I am making sense. Just one thing which I am trying to illustrate here is that whenever we are approaching towards the left hand side, if you will try to observe the picture here, we are dividing or multiplying, in other words, by 1 by 5, and on the right side we are multiplying with the 4 by 5, because that is a kind of a recurrence relation which is given to me, and the cost which is required to do so is n. Now again, the cost required to split this is, if suppose I am splitting n elements into two halves, cost required is n. So when I am splitting n by 5 elements into two halves, the cost required will be obviously n by 5. And similarly here also it will be 4n by 5. So total cost required in the second level will be 4n by 5 plus n by 5, so it will be equals to n. Similarly here, if you will try to observe, again a split will happen into two halves, into two halves, into two halves, and again we will try to calculate the cost, and again if you will do the summation of that, you will get the value as n. Means one thing we are observing, that at every level, we are having some sort of cost. But overall, in a nutshell, the total cost required will be equals to n. Second thing that we are observing is that when we are moving towards the left side of a recursive tree, we are multiplying our value or our data elements by 1 by 5. And when we are moving towards the right side, we are multiplying the values by 4 by 5. And this is a kind of a recursive tree that we are generating here. This is a kind of a recursive tree that we are trying to generate here, right? Now, the question is again same. Until what point of time do I basically generate this recursive tree? Until what point of time? I have to stop, right? At one point where there is only a leaf node. So, obviously, what is the base case condition? When the value of n is equals to 1 in my recursive tree. It means that when I'm going towards the left side, it will be n by 5 to the power k. When it will be equals to 1, it will stop. It means that the value of k for the left part, I would say, I will say it will be equals to n, which is equals to 5 to the power k. So the value of k here at the left part will be log of n base 5, right? Log of n base 5. Whereas on the right part, if you will try to observe here, on the right part, what we are trying to do is that we are trying to basically getting the value as n by, can I write like 5 by 4 on the below position? 5 by 4 to the power k, which is equals to 1 here. Now here if we will try to solve this, we will be able to get the value of n as 5 by 4 to the power k and the value of k as log of n base 5 by 4. This is the value of k that we are getting for the right part. Now we all know that we are trying to compute here the big O time complexity, right? So we should know that what is the higher value, what is the higher factor, that only we can take, because if I am taking a higher factor, automatically lower factor will automatically be covered up. If you remember in one of the session, I have already told you that whenever we are comparing a logarithmic part in the complexity classes, I remember I have talked about this thing, that whenever we are comparing a logarithmic part, for example log of n, and there are two bases that we have, for example here we are having 5 and here we are having 10. So a log having a smaller base is having a greater value. This is the major thing that you should know. Again, this comes under the properties of logarithmic, which I am expecting that everyone is aware of as of now. So here if you will see what is having a lower value, which base is having a lower factor, obviously 5 by 4. It means that this is something which is having a overall higher value, right? It means that until k number of levels, how many number of levels we will do split? It will be log of n base 5 by 4. It means k levels. And at every level, what is the cost associated with that? It will be n. So what is the overall time complexity? So either we can do what? We can add until k number of times the effective cost, or now we know the value of k and we also know that at every level how much cost is required. So we can directly multiply also. It seems like this, that suppose you are having maybe 10 toffees, okay? You are having 10 toffees. So here what I am saying is that what you are trying to do, that for example, you are splitting your toffees into 5 students and each student is getting 2 toffees. The number is same. So if you want to count how many number of toffees are there, so what you can do is that you can do with the help of two methods. Either you can count this 2 values 5 number of times, 2 plus 2 plus 2 plus 2 plus 2, and you will get the value as 10, right? Or what you can say to me that why to add until 5 number of times? What I can do is that I have 5 students and each one is having 2 toffees. So I can get the same value as 10 until this method as well, right? Very simple. So what I'm saying is that this 5 is something which you can consider in our tree is the value of k, which indicates that number of levels, right? Number of levels. And this 2 is something which you can consider is the cost, which is the value of n. So either you will add that n until log of n base 2 times, or you can do the simple multiplication. In both of the ways, you're getting the same value. So here, why is that so? Because you are having a same toffees. You are providing the same toffees to everyone. In other words, you are having a same computational cost at every level. That's why you will get a overall time complexity as order of n multiplied with log of n base is 5/4, because that is having a bigger value. So that is the overall result or the answer for this particular approach. So I hope that everyone is able to get an idea that how basically with the help of a recursive tree approach, we can solve any kind of problem. Basically, we have to create this recursive tree. In this recursive tree also, we need to calculate that how many number of levels do we have to create, and at every level, what is the effective cost. Either if the cost is different at every level, suppose here it is n is coming, here some other n/2 or n/4 is coming, here is something n/8 is coming. At that point of time, you need to add every cost until k levels. But here, because the cost is same, so we can directly multiply as well. I hope that I am making sense to everyone. If you so in this particular session, we will talk about another problem for recursive tree approach. Let's get started. I hope that by seeing the previous problem, you will get actually a sense that how we can solve from end to end any recurrence relation using a recursive tree approach. The very important point that we have understood in that session is that recursive tree approach is applicable only when we have multiple recursive trees, or only when we have multiple recursive terms, I would say. Let's talk about another example. For example, you have been given that the t of n, where when n is a small problem, the value is constant. But when n is a big problem, when it is greater than 1, then it will be equals to t of n/5 plus t of 3n/5 plus n. This is a kind of a problem that we have. Now, this recurrence relation which is given to us is what we need to solve here. How we can solve? Just try to see this very much carefully. So again, if you will see here, we are having more than one recursive term, right? So this can be solved with the help of a recursive tree approach only. Recursive tree approach only. So how we can do so? What we can try to do is that we are having the value of t of n as t of n/5 plus t of 3n/5 plus n, right? Means what we are trying to do is that we are trying to split our data into two halves. N is splitting into two halves. On left side we are having n/5. On right side we are having 3n/5. Now the cost required to split this data into two halves again is something which is equals to this value, which is equals to n here. Now again here, if you will see in the next level, we will again try to split it into two halves. So we will be able to get the value as n/5 square and 3n/5 square. Now how I am doing so? Again, I am just looking the pattern. Here the pattern says to me that on the left side, on the left part, do the multiplication with 1/5, right? And on the right part, just do the multiplication by 3/5, right? And everything will be resolved here. Again, here also what we try to do is that we will say 3n/5 square, and here we will say 3 square n/5 square, and so on. The same thing will continue until some level k. Now the cost required to do this task is n/5, and here also it will be 3n/5, because when we are talking about the n level and when we are splitting into two halves, the cost required was n. So for the further splits, it will be n/5 and 3n/5. So what is the total cost required in the second level? It will be nothing but is equals to n/5 plus 3n/5, which is equals to 4n/5. If I will try to again do the further splitting, so here you will see that when you add all these terms, you will be able to get 3 and 3 is 6, 6 plus 9 is 15, plus 1 is 16. Means what you are getting is 4 square n by 5 square. It means that at every level, we are having a different cost, right? At every level, we are having a different cost. This is the first thing that we have observed. Unlike the previous case where we have seen that on all the levels, we are having the same cost, which is n. In this case, we are having a different cost at every level, right? N for n by 5, 4 square, n by 5 square. That's true. Now, on the left side, we are observing one pattern that we are dividing the values by 5. On the right side, we are observing another pattern where we are multiplying it by 3 by 5. Okay. Now we have to see that which level is the higher level. So until that point, I will take up, automatically the lower level will be covered up. Okay. So on the left side, if I will observe here, what I am trying to do is that I am trying to do n by 5 to the power k, which is equals to 1, because 1 is the base case condition, the termination condition. So here the value of n is equals to 5 to the power k, or the value of k is equals to log of n base 5. This is the first k value which we are getting for the left part of our division, of our recursive tree. So this is a kind of a recursive tree that we are forming up here. Recursive tree. Now let's move ahead towards the next part, where what we are trying to do is that we are trying to majorly looking towards the right side, where what we are trying to solve is, we are saying it will be n by, it will be 5 by 3 to the power k, n by 5 by 3 to the power k, which is equals to 1. So here the value of k is looking to be log of n base 5 by 3. So this is the second value which we are getting here. Now can anyone tell me, this is the first level, this is the second level that we are getting here. Which particular level is having a higher value? Which particular level is having a higher value? Here if you will observe, lower the base, higher the value. It means that this is having a high number or high value. But now here if you will try to observe, we got the answer that it at max, it will reach until this log of n base 5 by 3 level. This part we have understood. But now here if you will observe, in this particular case at every level cost is different. At every level cost is different. So you can't multiply directly by saying order of n into k, just like the way we did previously in the previous problem. In previous problem, at every level the cost is same, if you remember. Here at every level the cost is different. So we need to manually add at every level the cost requirement. So can I say that at the first level it will be 4 by 5 to the power 0, which is 1 into n. At next level it will be 4 by 5 to the power 1 into n. At the very next level it will be 4 by 5 to the power 2 into n, until so on. We will reach the last level, and the last level is having a value of k as log of n base 5 by 3 into n, right? This is what we are getting. Now what we can do is that we will try to take n value as common, and we are saying 4 by 5 to the power 0 plus 4 by 5 to the power 1 plus 4 by 5 to the power 2 until so on 4 by 5 to the power log of n base 5 by 3. Here if you will see, this is a. A is the first term that we have, which is 4 by 5 to the power 0, which is equals to 1. What is the common ratio here? Common ratio is 4 by 5, right? And this forms a, why I'm asking these questions, because this is forming up a GP series. This is forming up a GP series. Okay, that's perfectly fine. Now, in this GP series, the value of R is less than 1. So, what is the sum of a GP series when the value of R is less than 1? It will be equals to A into 1 minus R to the power n divided by 1 minus r. That is what we have whenever we are talking about a GP series, right? Now, you just need to try to solve by taking 4 by 5 as the common ratio, the logarithmic term, and 5 by 3 is the number of terms that we have, divided by 1 minus 4 by 5 into something which we called as n, because n is something which we already have in our computation matrix. Here, if you will see, when we try to do the computation here, this particular term, when you will try to just impute the values, you will get this term as a constant. So that will be resolved in constant time complexity into n. So the overall time complexity you will again able to get here as well as order of n, So again, if you will try to observe here, starting from the scratch until the very end, it's just that we have to first of all form a recursive tree. We have to find the maximum value of k. We have to see that is the cost requirement at every level is same or different. If it's different, we just need to add all of them until the value of the k. Otherwise, we can directly do by saying order of k into n, just like the way we did in the previous session. That's all. And after solving the series, you will always get some number which will suggest you a bigger time complexity. And that's the approach to solve any recursive tree approach. That's the way to solve, I would say, any recurrence relation using a recursive tree approach. I hope I'm making sense to everyone. So in this particular session, I'll talk about problem number 3, which is based on recursive tree approach. Okay, we'll try to solve this problem as well, so that we will be able to get a very clear understanding and the insights about recursive tree approach. So let's get started. For example, a recurrence relation is given to me. A given recurrence relation is, so a recurrence relation is given to us, which indicates that the value of t of n is something which is equals to 1 when I am having the value of n is equals to 1, and when the value of n is greater than 1, at that point of time it is something which is equals to t of n by 2 plus t of n by 3 plus, let me write it further here, t of n by 5 plus c, when the value of n is greater than 1. This is a kind of a recurrence relation that we have. Now, the important point here to understand is that here we are having 3 different recursive terms. Until so far, the problem number 1 and the problem number 2, which I have discussed based on recursive tree approach, we have seen that only 2 recursive terms were there. But here we are having 3 different recursive terms. But it's not an issue. Why? Because here again, if you will see, instead of making that binary kind of a tree, we are making ternary kind of tree. That's the only difference that we have here. So we are having this n number of elements. We are dividing the number of trees. So here the element is split into 3 halves, where first half is n by 2, second half will contain elements as n by 3, third half will contain n by 5. Now the cost required to do this particular split is, we can say as C, right? We are doing a splitting into 3 halves, n by 2, n by 3 and n by 5. Now here if you will see, just observe one thing. On the left side we are multiplying our data or the elements by 1 by 2. In middle we are multiplying with 1 by 3. In the right we are multiplying with 1 by 5. So the same thing we are trying to do here with the same approach. So here the cost requirement will be, because here in the first case when I am dividing my n into 3 halves, the cost requirement is C. So it means that when we are dividing our n by 2 into 3 halves, n by 3 into 3 halves and n by 5 into 3 halves, each is having a cost requirement as C only. So in total the cost will be 3C, right? So here it will be n by 2 to the power 2, here it will be n by 2 into 3, here it will be n by 2 into 5. Similarly here it will be n by 3 to the power 3 into 2, because on the right side, on the left side multiplication by 1 by 2, in the middle multiplication by 1 by 3, in the right multiplication by n by 5. Similarly here as well, n by 2 we can say, n by 5 into 3 we can say, and n by 5 square, and so on. Now here if you will see, if you will try to observe the pattern, at each and every time, here the cost again, there will be a 3 times splitting will be done, here as well, right? Here as well, here as well, here as well, here as well, and here as well. Now here it will be nothing but is equals to 3 to the power 2c, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9c. The question is that now instead of having only the left hand and the right, in this recursive tree that I have created here, so in this particular recursive tree that we have created just now, the question is how many different kinds of splits that we have. So when we are having a left side, in that particular case, what we are trying to do is that we are saying n by 2 to the power k, which is equals to 1. So here the value of n is equals to 2 to the power k. So here the value of k is equals to log of n base 2, right? This is what we are getting. If suppose we are talking about the middle one, if suppose we are talking about the middle side, at that point of time, we are saying that we are having n by, what we can say, 3 by k, 3 to the power k, because at each and every time in the middle portion, we are dividing the values by 3 by 3 by 3 and so on, which is equals to 1. So here the value of n or the value of k is something which we are getting as log of n base 3, right? And on the right side, if you will observe here, what we are getting the value as, we are trying to do the split on the basis of n by, I would say 5 to the power k, which is equals to 1. So here again the value of k is equals to log of n base 5. So here we are getting 3 different values of k. One is something called as log of n base 2. One is something called as log of n base 3. One is something which we called as log of n base 5, right? Now the question is that which particular value of k is higher value, which is having a lower base. So can I say that this is something which is having a higher value? Yes, out of these 3. And at each and every time we are doing this, so at every level, so we got the level, maximum level is log of n base 2. And each and every level, we are getting the power addition by 1. So in total, what we can do is that we are saying that it will go, we can take c as common, 3 to the power 0, plus we can say 3 to the power 1, plus 3 to the power 2, plus 3 to the power 3, until how many number of levels it will go? It will go until value of log of n base 2. Log of n base 2. So here the value of a is equals to 1. Here the common ratio is 3, right? So it's a GP series where the common ratio is greater than 1. So in that case, the sum of the GP series will be a into r to the power n minus 1 divided by r minus 1. Here the value of a which we are getting is 1 only. The value of r is 3. The value of n is log of n base 2 minus 1 divided by 3 minus 1. I have just imputed the value. And outside that, we are having the value as c. Outside that, we are having the value as c. If you will try to solve this, you can take the value of n here at the upfront and 3 at the log of 3 base 2 minus 1 divided by 2 into c. In terms of big O, I can say that you will get value approximately n to the power 1.5. So this is something where you can say that this is a big O time complexity, which is, you can also write it as big O of n square, right? So this is the overall way to solve any recurrence relation using, again, recursive tree approach. Here, how this problem is somewhere different from the previous problems and why I introduced this problem. The major objective here is to make you guys understand that yes, here if you will observe, we are having 3 different kinds of recurrence relations, right? Recursive terms are there. That is 3. Now, I hope that if you are getting 4, 5, n number of times also. It's just that you have to create a tree accordingly, and then you will be able to clearly calculate that what is the value of k. Here, if suppose you are doing a binary split, you will be able to get 2 k's. Whichever is having a higher value of k, that you can pick up. Apart from that, if suppose you are doing 3 times split, accordingly you will have 3 values of k and so on. It means that the value of k, how many number of values of different k's you can get, it depends on how many number of splits you are doing for a tree, for a recursive tree. And accordingly you can calculate. And finally, you will be able to get the overall big O time complexity by solving just a GP series. Here you can also have a AP series as well. It's just that you should know that what is the formula to compute the sum of AP series or the GP series that you are getting here. I hope that I am making sense to everyone. So in this particular session, we will talk about Master's theorem. I hope that everyone is clearly able to see my screen on the board. Here, I just want to tell you that, first of all, where this Master's theorem is applicable. Again, this Master's theorem is basically helps us to solve any kind of a recurrence relation. Until so far, if you guys remember, we have discussed 2 different methods to basically solve any recurrence relation. One is we have talked about a substitution method, and we have solved a lot of variety of questions there to see that how basically substitution method will work. After that, we have talked about a recursive tree approach. There also, we have seen that how basically we can first of all create a recursive tree, and with the help of that, how we will reach to a big O time complexity solution. After looking into that part as well, this is the last part where I want to tell you that the recurrence relation can also be solved using a Master's theorem, but under some constraints that you have to take care. First of all, your recurrence relation will look like this. So whenever you are trying to apply any Master's theorem, you should take a note that your recurrence relation will be of a form like this, where we are again having a single recursive term. For example, here you can see this t of n by b is a recursive term, and here this a is some constant and b is also some constant, and f of n is some function which is, I can say, is a positive function. Now, what is the constraint? As I told you that a and b are the positive constants, and the value of a should be either less than or equal to 1, or the value of b is greater than 1. Now, this f of n can be represented in this form, where I am writing it as n to the power k log to the power p n. Now it depends what kind of recurrence relation will be given to you. I will for sure demonstrate you various examples with the help of which we will be able to understand all these different cases. Now this thing which I have written here, you will find in various standard books this kind of cases which they have written in their Master's theorem. Actually, don't need to be afraid about all these cases. These are very simple. I will try to demonstrate you in such a way that you will be able to do it very much fastly. But let's try to understand what I have written here. So first of all, whenever you want to apply any recurrence relation, you need to calculate a very first thing, which is the value of log of a base b. Okay, this is the first thing that you need to evaluate. For example, if suppose I am writing 2tn by 2 plus 1 or plus 1, okay. So this is a recurrence relation that is given to you. T of n is equals to 2tn by 2 plus 1. Now in this particular case, you have to see what is the value of a. It is 2. Just try to compare this equation with the first standard equation which I have marked in green pen. Here if you will see, the value of a is 2 and the value of b is also 2. Now this is something which we are saying is f of n, right? Which we want to represent in the form of n to the power k log to the power p into n. Now because this value is 1, it simply indicates that the value of k is equals to 0 and the value of p is also equals to 0, right? We will try to understand each and everything, but as of now, try to see what I want to infer here. That what is the meaning of a, what is the meaning of p, what is the meaning of f of n, and from that f of n, how we can compute the value of k and p. I hope it's quite simple. So the very first task here is to compute the value of log of a base p. For example, for this particular recurrence relation, my value will become log of 2 base 2, which will be equal to the value as 1 here, right? Which will be equals to 1 here. Now, we need to compare the two values. One is the value of k, another one is the value of log of a base b that you have evaluated. So the second thing is that you need to compare the two values, that is log of a base b that you have evaluated and the value of k, which you will get from function f of n, which you will get from the function f of n. Now, there can be three cases that you can get. Either the value that you have evaluated log of a base b is greater, or it is equal, or it is lesser. On the basis of that, we have three different cases in our master's theorem. The very first case, try to understand. Here in this particular case, the example which I have just shown you, the value of log of a base b is, I believe, 1. The value of k is 0. You can clearly see that this particular situation falls under the category of case number 1, where the value of log of a base b is somewhere we are getting as 1, because we are solving a recurrence relation which is saying that, so this is, you can illustrate it as example number 1, which I want to explain you. So here we are having 2t n by 2 plus 1. This is a recurrence relation that we have. The value of t of n is something like this. Now, the value of log of a base b is equals to 1, and the value of k which we have evaluated is 0. So this clearly falls under the category of case number 1. And case number 1 says that if you are falling under me, your answer should be directly big O of, or you can say theta also, big O of or theta of, let me write in the form of a big O, because we will always talk about worst case time complexity. It will be nothing but the value of log of a base b, which is nothing but is equals to order of 1. So here if you will see, what we are saying is that, so this is order of n to the power log of a base b is the final answer. This is what you can refer from here as well. So it says that, it simply says that first of all, compute the value of log of a base b, compute the value of k, just try to compare what is the relationship. Either it will be greater or lesser or equal. Accordingly, it will fall under the category of case number 1, 2 or 3. Once you will be able to get an understanding of that, if suppose here if you will see, it is falling under case number 1, where the value of log of a base b is greater than k. In this case, your answer directly should be, you can write your result directly as n to the power log of a base b, or I can say the result will be order of n, because the value of log of a base b is equals to 1 here. So that's why you will be able to get a clear-cut answer. Here if you will see the way we are doing this thing, we have seen the substitution method as well, and we can try to use substitution method here as well, right? But substitution method took a lot of time, where we are solving a lot of series. It may be GP or AP, doesn't matter. But here if you will see, there is no series that we are solving. It's just that we have to consider that in what category or in what case our question belongs to, and accordingly we have the direct answer, right? That's why it's of much use and much ease to use as comparable to other recurrence relation methods that we have solved so far. So always remember, the very first thing to keep in your head is that whenever the value of log of a base b is greater than k, your answer is directly will be order of n to the power whatsoever value you are getting as log of a base b. I hope I am making sense. If suppose I want to give you some other example in the same format, it will be suppose 4t n by 2 plus, suppose I am writing it as maybe n. Suppose this is the equation that I am giving to you. Now again, what you need to do is that, so as of now I am intentionally considering those cases which belongs to case number 1. Maybe in the next video, I'll try to explain to you the case number 2 and then the case number 3. Case number 1 and case number 3 is pretty simple. Case number 2 is also very simple, but with the help of examples, maybe initially you will be very much ambiguity, but when you re-listen this video again, maybe you will be able to clearly understand the concept which I want to explain to you here. So here again, if you will see, the value of a is equals to 4, the value of b is equals to 2. Now again what we are trying to do is that we will try to find out what is the value of log of a base b, the very first step that we have. So it will be log of 4 base 2, it will be log of 2 to the power 2, right? This can be written as 2 log 2 base 2. This is 1, so the answer is 1. Now this particular function, this is f of n, which can be written as theta of n to the power k log to the power p into n. Here clearly we can see with the help of this demonstration, the value of k is equals to 1 and the value of p is equals to 0. Clearly we can say this, right? Now here we can clearly understand that the value of this log of a base b is somehow greater than the value of k, because this value is 2 and this value is 1, right? Again, because this is falling under again the case number 1, we can directly write that it is nothing but is order of n to the power log of a base b, which is square. So here for this recurrence relation, for the second case also, for this recurrence relation, our time complexity will be order of n square. So this you can consider as the example number 2. Any example which basically falls under the category where the value of log of a base b is greater than the value of k, you can consider right like this, right? If you want to get, if you want me to explain some other example, let me try to explain one last example where I can write it as t of n, which is equals to maybe 8t n by 2 plus maybe n square. Again, here if you will try to observe, the value of a is 8, the value of b is 2, right? And this can be written as n to the power k log to the power p into n. This function can be written like this. So clearly I can say that the value of k is equals to 2 and the value of p is equals to 0. Let's try to calculate what is the value of log of a base b. It will be log of 8 base 2. This can be written as log of 2 to the power 3 base 2. It can be written as 3, we can move ahead, log of 2 base 2. Now this again can be equals to 1. So the answer is equals to 3 here. Now again if you will try to understand here, the value of log of a base b is somehow greater than the value of k for this question as well, intentionally, because I am picking like that kind of example only. Here if you will observe, this value is 3 and this value is 2. That's why this relationship holds. That's why our direct answer will be n to the power log of a base b means order of n cube. This is how you can solve any kind of question. The first thing is that in Master's theorem, you have to see that whether the recurrence relation is following the above pattern or not. This one. If it is following that pattern, you have to recognize the value of a, b, k and p. 4 things you have to evaluate. Then second thing, you need to calculate what is the value of log of a base b. Once you will be able to get that value, you need to compare that value with k. As of now, we have discussed only case number 1, where I am saying that if suppose the value of log of a base b is greater than k, at that point of time, your answer is directly equals to n to the power log of a base b. I hope with the help of these 3 examples, I am making sense to everyone that how basically I am saying it will be order of n or n square or n cube, right? Directly, how am I writing? Just you have to see these cases. And in this also, just as of now, refer case number 1, because that's what I have illustrated with you all in this particular session. Let's try to take a break now. Just try to see whether you are able to get all these examples or not. I want to give you some time. Let's meet you all in my next upcoming video, where I'll talk about the next case number 2, where we will deal with the 3 different cases that we have. So in this particular video, we will talk about case number 2. I hope that before coming to this session, you already have watched my previous video, where specifically I have talked about various examples on case number 1. So what we have covered up so far? We have seen that Master's theorem is only applicable if we have this kind of recurrence relation, as you can see on my blackboard. Afterwards, we have seen that if suppose the value of log of a base b, which is the very first step to evaluate, is greater than the value of k, we can directly write the answer or the bigger time complexity as n to the power log of a base b. We have covered a few examples as well, just to give you a overall background of that. We have seen that, for example, we are having a recurrence relation like this: 9t(n by 3) plus maybe 1. Suppose this is a recurrence relation which is given to you. So what we try to do is that, first of all, we will try to write this value of 1 in the form of a f of n, which is nothing but n to the power k log to the power p into n. With the help of this, we will be able to get an idea that the value of k is somewhere equals to 0. And the value of p is also equals to 0 here. Okay, we are getting the point. Now we need to calculate what is a, it is 9, what is b, it is 3, and then we calculated the value of a log of a base b. We are getting that value as log of 9 base 3, that is equals to log of 3 to the power 2, base is 3. So we are getting here the value as 2 only, right? This is what we are getting after evaluation. Now that is where we came under the category for the case number 1. Why I am saying case number 1? Because here we need to compare the value of log of a base b and the value of k. And by comparison only, we will be able to get an idea that this value 2 is somehow greater than value of 0. And whenever this case we encountered, we already discussed that time complexity is n to the power whatsoever value you are getting as log of a base b. Here we are getting as 2, so it will be equals to n square. So this is our final time complexity that we are getting. Now in today's session, we want to discuss about the case number 2. Case number 2 says that suppose the value of log of a base b is equals to the value of k. At that point of time, what will happen? That's the scenario that we want to discuss now. So here, if you will see, let me try to take another recurrence relation that I have. For example, here we are having the value of t of n as 2t n by 2 plus 1. Suppose plus 2t n by 2 plus n. This is a recurrence relation which is given to us. Now let's try to understand here that what is the value of a. So here we can see that the value of a is 2 and the value of b is also equals to 2, right? I hope that this is making sense to everyone. Now can anyone tell me what is the value of k here? So here if you will see, it will be n to the power k log to the power p into n. So I can clearly state here that the value of k is equals to 1 and the value of p is equals to 0 here. So what is the value of log of a base b? The value of log of a base b is log of 2 base 2, which is equals to 1. It means that here the value of log of a base b and the value of k is equals to 1. It's not like this case, right? That's why it's falling under case number 2, where now it's very important for us to understand that what is the value of p that we have. So here if you will see, first of all, this is case number 2, where we can clearly see that the value of log of a base b is equal to the value of k, which is equals to 1. And the value of p is equals to 0. It means that the value of p is greater than minus 1. In that particular case, what will happen? It simply says that your result will be theta of n to the power n log n. Here, if you will see, it is nothing but, because when the value is greater, it will be n to the power k log p plus 1 n. So that's why I am saying n log n. Why? Because here if you will see, what is the value of k here? It's 1, right? It's 1. So here we are saying it will be theta of, or big O also you can write, n into log p value is 0 into n. So this value will come out to be n log n. It means that, now let me try to simplify this thing. Without seeing the above definition, you can also try to solve it. Try to listen this point very much carefully. Whenever you are getting the value of log of a base b equals to the value of k, whenever they both are equal, right? In maximum cases, your value of p is positive or greater than minus 1. At that point of time, what you have to do is that whatsoever with the number mentioned here, whatsoever be the number mentioned here, this n, just try to multiply it with the log of n. For example, suppose here it is n square. Suppose here it is n square. Let me write here. Then your answer will be theta or big O of n square into log of n, if suppose the values are same. So whatsoever be the value you are having on the f of n, you have to multiply it with the log of n whenever the value of log of a base b is equal to the value of k, given the value of p is greater than -1. Let me try to take another example. For example, what I want to state here, for example, here you are having t of n, which is equals to 8t n by 2 plus, suppose I am having n cube here. Now again, here if you will try to see what is the value of k that we have, the value of k is 3 and the value of p is equals to 0. Now again I'm not writing the value of f of n. I hope that everyone knows how I am computing these values. Now what is the value of log of a base b? It is nothing but is equals to 3. Again, these two values are equal. These two values are equal. And because these two values are equal, so what we can do is that we can directly say, or we can directly write without any reference to the above equation, you can directly write whatsoever be the value of f of n, which is n cube, into log of n. That's what I want to state here. Whenever the values are equal, you can say that the value of p is greater than -1 as well. So you can directly write whatsoever be the value of f of n that you have into log of n. That's what I want to state here. Very important point and very easy to understand, right? You can just compare also. What I have written, that value should be n to the power k log to the power p into n. So here if you will see log to the power p plus 1. So here you will see k is 3 only, n to the power 3, log is 0, 0 plus 1 is 1 into n. That's what I am saying, directly write it down. One and the same thing. Now the problem comes when you are having a value of p which is less than -1, right? Which is less than -1 or equal to -1, because we are having three cases here. Until so far, we have talked about only this case. Until so far, we have done with this case. But now when the value of p is equal to -1, let's try to understand that example as well. So I can say that this is example number 2 for case number 2. Sorry, example number 1 for case number 2. And this is example number 2. And I have explained you in a little bit better manner as well that how you can directly write these things. Let's talk about another example number 3. Example number 3. For example, here I am saying that the value of t of n is equals to 2t n by 2 plus, now I am writing it as n by log of n. Suppose this is the equation that I have. Here if you will see, the value of log of a base b is equals to 1. The value of k is also equals to 1 because n to the power is what? 1 only. What is the value of p? It is nothing but -1. How? This term which I am writing here can be represented as n log of -1 into n. And f of n can be represented as n to the power k log to the power p into n. So k value is 1, p value is -1. We can write it like this, right? So here in this particular case, this is what the values which I am getting here. Now we came under the category of p equals to -1. At that point of time, the value will be equals to n to the power k log of n. So here it is nothing but order of, what is n to the power k? So whatsoever value is written here, you have to write log of n with that. So instead of multiplying with the value of log of n, whenever you are getting the value of p as -1 here, your value will be equals to, you need to multiply it with log of n, right? So here, whenever the value is equals to -1, you need to multiply it with log of n, right? One another example which will illustrate you the another case as well, which is when the value of p is less than -1. This is the case which I want to discuss about now. Let's take the example number 4 here. Example number 4. I hope with this, the case number 2 sense will be pretty much clear to everyone. Suppose it will be 2t n by 2 plus n divided by log 2n. Suppose this is the case that we have. Again, if you will try to observe here, the value of log of a base b is equals to 1. The value of k is also equals to 1. But the value of p here, if you will write it like this, you can write it like n to the power log minus 2 into n. So the value of p is equals to minus 2 here. It means that this value is somehow lesser than minus 1. It means that we are coming under the category of case number 2, and in that also case number 3, right? For that particular case, what is the value that we are getting? So it says that whenever you are getting into this category, it will be something which is equals to n to the power k. Now, what is this? K, it is 1. So when you are getting, this is a very, rare case which you will find, but still you should know everything pretty well end to end. So whenever you are getting this kind of scenario, you just have to take directly the value of above 1, which is n to the power k only. You don't need to multiply anything like log of n or log of log n. Right? That is the simple concept which is what I want to tell you here. So there are 3 cases which we have understood. One case, so in all these 3 cases, one situation is common, which is that the value of log of a base b is equals to k. If that is true, in that particular case, maximum number of time you will get the value of p as 0. Means you will get the case when the value of p is greater than minus 1. In that case, you can directly pick up the value of f of n and multiply that value with the log of n. Just like the example number 1 and example number 2 which I showed you. We directly picked up the value of f of n, which is n, and multiply it with log of n. We directly picked up the value of n cube and multiply it with log of n, right? In example number 3 and example number 4, here you can see that either the case will be p is equals to minus 1. When this kind of situation will happen, what you have to do is that you just need to multiply the value with log of n instead of simply multiplying it with log of n. And when you're getting a case when the value of p is lesser than minus 1 as well, in that particular case, you just don't need to multiply with anything. It's just theta of that function of n with a positive number, n to the power k. So it is nothing but theta of n to the power k. That's what I have written here. This is what you're getting here as well. Theta of n to the power k, right? So I hope that the thing which I want to explain you here with the case number 2, with all these 3 cases where the value of p is greater than minus 1, equal to minus 1 and less than minus 1 is pretty much clear to everyone. So in this particular session, we will talk about the last case of our master's theorem. What's that case left? When the value of log of a base b is less than k. So far in our previous 2 videos, I hope everyone already have watched, we have seen the case number 1 and case number 2, where either the value of log of a base b is greater than k or it is equal to k. Now in the last part of the session, we will try to discuss that what will happen when the value is less than k. It's quite simple. Let me try to take one example, and with the help of that, I'll try to demonstrate you. For example, here we are having the value of t of n, which is equals to 2t n by 2 plus, I would say, n square. Now in this particular example, if you will try to find out what is the value of log of a base b, here you are getting the value as log of 2 base 2, which is equals to 1, which is for sure lesser than the value of 2, because the value of k here, as you can see in this function, is equals to 2, right? So in this particular case, this case number 3 will lie, where the value of log of a base b is less than k, right? Now, what is the value of p, by the way? It is equals to 0 here. So basically, when the value is less than k and the value of p is 0, what it is saying? That it's just that theta of n square. So always remember that whenever, without referring the above thing I am telling now, just try to evaluate what is the value of log of a base b and what is the value of k. Whenever the value of log of a base b is lesser than the value of k, what you need to do is that you need to directly just put the value of f of n. Whatever be the value doesn't matter. Whatever be the value doesn't matter. It's just that the value of p should be greater than equal to 0. For example, here instead of n square, you are having n square log of n. For example, you are having 2t n by 2 plus n square log of n. So what will happen? You will again try to find out what is the value of log of a base b. Again, you are getting the value as 1, which is less than the value as 2. So what you are getting the value as directly, you can directly just copy paste the value of f of n here. That's what I want to state here. Here if you will see, it is nothing but n to the power k log of Pn. That's what we are getting here as well. You can just directly fetch up the value of f of n and you can directly write it like this, right? Another example, for example, you are having the value of t of n as 4t n by 2 plus n cube divided by log of n. Okay, this is the value that you are having here. Now here the value of a is 4, the value of b is 2. Again, if you will try to evaluate what is the value of log of a base b, it is nothing but is equals to log of 4 base 2, which is equals to 2. Now the value of k is something which is equals to 3. Again, the value of log of a base b is somehow less than the value of k, right? In this particular case also, what you can see is that it is falling under the case number 3. But here the value of p is equals to -1, which is less than 0. So what you need to do is that you just forget what is the below portion it is written. You can directly take the value of n cube. That's it. Theta of n cube or big O of n cube. So it is saying take the value as n to the power k. That's what I am saying here. So in a nutshell, for a case number 3, what you need to do is that whenever the value of log of a base b is less than the value of k, if this is the constraint that you are getting here, what you're supposed to do is that you're supposed to see that what's the value of p. Instead of looking into that also, what you can do is that you can just say order of f of n. Directly you can write. If suppose you're having some number which is -1, the value of p is -1. At that point of time, what you can do is that you can directly skip that negative part and take n to the power k directly. That's the overall idea behind the Master's theorem that we have understood. With this, we have learned specifically what Master's theorem is all about. We have learned how we can get the value of a, b, k and p. We have learned the case number 1, case number 2 and case number 3 in a nutshell with all these 3 videos. I hope that I'm making sense to everyone that how this Master's theorem will work. In the future sessions, whenever we are getting a recurrence relation of this green type, we will always try to apply the Master's theorem because this will take a lot of lesser time as comparable to the substitution method. That's the only reason I will apply a lot of times this Master's theorem. So always have this thing in your head. Don't get worried because when you do the practice, a lot of times you have the habit and everything will be in your memory after some point of time. If it's new for you, I will suggest to everyone, practice as hard as you can, okay? The only way to succeed is the practice, right? So if you will practice these questions, take more questions of the recurrence relation, which can be solved using the Master's theorem, try to apply, try to see whether you're getting a correct result or not. Specifically in GATE competitive exam, you will get this kind of questions a lot. So you can refer the previous year GATE questions, which will help you to get a better insight of how we can solve any recurrence relation. Because now, knowledge-wise, you know, it's just the practice that is required, which I suppose that you can do. In the next upcoming video, I will also try to give you some practice set questions, which will help you to check your knowledge that whether you will be able to get a clear-cut idea or not of the complete Master's theorem that we have discussed as of now. So now I hope that you will be able to understand the concept behind substitution method, recursive tree method and the Master's theorem. If you do, please hit like button, share this video with each and everyone who is looking for this kind of a concept, right? And I'll very soon see you all in the next upcoming videos. Bye bye everyone, and do subscribe to my channel as well. Bye bye.